Okay, let's talk about nuclear fission and fusion. So what's the difference between fission and fusion? Well, fission is where you are breaking apart larger things into smaller things. And fusion is where you are bringing together smaller things into larger things. And in 1932, John Cockcroft and Ernest Walton used something called a particle accelerator to produce high-speed protons. And because of their high speed, protons also have really high kinetic energy. And those protons collided with a lithium nuclei, and they were able to penetrate and disrupt the lithium nuclei, which resulted in an artificially induced nuclear reaction. And in this nuclear reaction, which was caused by accelerated protons, the lithium nucleus was split. And the result was two nuclei, which were both helium. And the newspapers reported that Cockcroft and Walton had split the atom for the first time. And an important observation from this experiment was that when the kinetic energies of two helium nuclei, which are alpha particles, are added up, the total kinetic energy was actually greater than the kinetic energy of the proton that caused the reaction to happen. But the combined mass of the alpha particles was less than the masses of the proton and the lithium atom combined. So this confirmed a prediction made by Albert Einstein that mass could be changed into energy. And he related mass to energy with his famous equation, E equals mc squared. And what actually happened in the nuclear reaction induced by Cockcroft and Walton was that mass was converted into energy. And the same year as Cockcroft and Walton carried out the first artificial nuclear reaction, Chadwick bombarded beryllium with alpha particles that had been accelerated. And the helium nucleus was absorbed by the beryllium nucleus, and he formed carbon atoms and a new particle, the neutron. And energy was also released in this reaction. This was how Chadwick actually discovered the neutron. And this and other nuclear reactions can be used to produce free neutrons, which are now used as nuclear bullets. And fast-moving neutrons go right through the nucleus without having much effect. Let's go to the next page. So slow-moving neutrons are another matter, and they can be absorbed by nuclei. And fast-moving neutrons can be slowed down by passing them through heavy water or graphite. And that slows the neutrons down enough to let them react with another nuclei. So heavy water and graphite, when they're used in this way to slow something down, they're called moderators. And let's go on to nuclear fission. In nuclear fission, if the electrical forces overcome the nuclear forces, the nucleus can break apart. And this is called nuclear fission, which was discovered by teams of scientists working independently within days of each other. Otto Hahn and Fritz Strassmann observed this reaction in 1939. And you're going to get the release of very, very large amounts of nuclear energy because you're converting mass into energy according to Einstein's equation. And for every fission that occurs, 2 or 3 neutrons will be released. And then those neutrons are going to initiate even more fissions, which produce even more neutrons and more fissions. And then you possibly get something called a chain reaction. So if we go to the next page, and you take a look here. So there's a certain minimum mass that you need to have, known as the critical mass, before a chain reaction can occur. And if the needed critical mass is achieved, you can get an explosion of incredible force. And in a nuclear bomb, 2 or more subcritical masses of uranium-235 are actually forced together by an explosive, and the bomb explodes. Now let's talk about harnessing nuclear fission here. So the rate of fission can be controlled. And harnessing the energy released is a really useful tool. And the key to slowing down this reaction is to actually control the rate at which you're producing neutrons from this fission reaction. So if the rate of production can equal the rate of the neutrons being used, then you're going to have a self-sustaining reaction that happens. But you have to put a moderator into the reaction. Usually it's water, sometimes it can be graphite, sometimes it can be heavy water, which is deuterium oxide. And that's where you have hydrogen atoms and 2 neutrons. And if you're able to control the reaction, the nuclear reactors become a way for generating electricity. And they do that in Canada, the United States, and other countries. And other smaller nuclear reactors are used for medical and research purposes. But nuclear reactors are currently based on the fission reaction. And the energy that's released is used to heat water into steam. And then that steam is going to turn a turbine, which then generates electricity. So there are 6 main components to a nuclear reactor, which are on the next page. Number 1 is fuel. Usually it's uranium oxide. Number 2 is they have to have a moderator. They have to have something to slow down the neutrons so that the chain reaction can continue. And they have to have control rods, which absorb neutrons to shut down a reaction. They have to have a coolant, a pressure vessel, which holds the fission reaction, a steam generator, which converts your steam to electrical energy, and then a containment, which is usually a meter of concrete to protect the reactor in case something breaks down. Now, there are different types of reactors, and each one is slightly different from another. But the 3 most common are going to be a boiling water reactor, which the US has, Japan, and Sweden, and a pressurized water reactor, which are also in the US, France, Japan, Russia, and China, and then a pressurized heavy water reactor, which is only in Canada. Now, to show you the details of each one, the boiling water reactor has a single loop, and the pressure vessel contains the fission reaction. So here is your pressure vessel here. And this is where steam is generated. You can see that here. And the steam is carried to the steam turbine, so it proceeds this way, and then to the generator that turns it. And the condenser cools the steam back into water, and the water is pumped back into the pressure vessel through here. Major concern with this design is that the liquid that's in the steam is radioactive. So if there's any leaks, that would mean that radioactivity is going to be released into the environment. Let's go on to the pressurized water reactor. So the most common type of nuclear reactor is the pressurized water reactor. And this is where the heated radioactive fluid from the primary loop does not come into contact with the steam and the liquid used to turn the turbine in the secondary loop. This is more efficient and it's safer than the one we talked about previously, but it's a lot more expensive to build. If you take a look at the can-do down here, this is what is in Canada, and this is a modified pressurized water reactor, And the primary loop uses heavy water as the moderator, and it's a higher cost, but it requires a lower concentration of uranium. And let's go on to talk about nuclear fusion here. So nuclear fusion is the opposite of nuclear fission. So if you have light nuclei, and they're forced within a distance of maybe 10 to the negative 16th meters of each other, the nuclear force, which is really, really strong, is going to exceed the electrical repulsive force, and fusion might occur. So if two like-charged nuclei get very, very close to each other without repelling, they have to be moving at really, really, really high speeds, which means they have a lot of kinetic energy, and that means there are very high temperatures involved. And these high temperatures are the temperatures that are typically found near the center of the sun and other stars. And fusion is the source of the sun's energy. And fusion that happens at really high temperatures is called thermonuclear fusion. And when these light nuclei fuse, there's going to be a loss of mass, and that lost mass is actually converted into energy. So the sun is actually losing millions of tons of mass every second. And the energy produced from this mass leaves the sun as electromagnetic radiation. That could be visible light or infrared. This is an example of a fusion reaction here. And the fusion reaction that takes place in the sun involves a series of steps. The net reaction is actually believed to be this one right here. Now, ordinary hydrogen nuclei are fused to helium with the emission of something called a positron, which is a positive electron. And the positive electron, positron, is the antiparticle or antimatter of an electron. It has the same mass, but an opposite charge. A dream of nuclear physicists is to master the process of fusion so that it can be controlled and used as a source of energy. Fusion is a clean process whose products are not radioactive, and people have achieved fusion on a very brief scale in the development of the hydrogen bomb, but the temperatures that you need to use a fission bomb are really, really, really high.